Welcome back, Applied Calculators. In this screencast, we take a look at higher order derivatives. And I'll just introduce a little bit of notation for us. If f of x is our function, and f prime of x is the derivative of that function, then f double prime of x is the derivative of f prime of x. So every time we take a derivative of a function, we put an extra prime near the name of that function. If we were to take the derivative of f double prime, we'd get f triple prime, and so on. But there's another notation that we use. If y is the function in question, then you have seen the dy dx notation, and that's a hallmark of the slope argument. Dy dx is supposed to look like delta y over delta x to remind us that a derivative is a slope. But when we go to talk about the derivative of dy dx, the notation on that looks like this, and that's just really, really weird. It's really, really weird. Okay, so a little bit about what we do and why we do it. So let's imagine that you've thrown some rock in the air, and that rock is flying in the following way. Right, so you're at the top of a 4-story building, you throw the rock in the air and you let it fall. So we could take the derivative of h, and if we take the derivative of h, we get this. But then we could take the derivative of that. We could take the derivative of the derivative and get this number. The question is, who cares? Well, this is the height of a rock, and that's measured in maybe meters, maybe. So the derivative of that is measured in meters per unit of time, per second. And the derivative of the derivative is measured in meters per second squared, because h is measured in meters and t is measured in seconds. So we have ways to interpret the two derivatives. If h is a function that measures height in meters, then h prime measures how h is changing, how the height is changing over time. H is a velocity function, and it's measured in meters per second. H double prime measures how h prime is changing over time, and it's measured in meters per second per second. When we talk about how velocity is changing, that's acceleration. And so sometimes these derivatives of derivatives have meaning for us, and it's up to us to try to find that meaning. Consider the following. Consider a business example. Let's pretend that you have some revenue function, R of x. We're selling some product and it's relating. So let's see, let's relate, here we go, 1 over 10,000 times, I don't know, 400 x squared minus x cubed. And I'll get really specific. X is going to be the number of thousands of dollars spent on advertising, and R is revenue in thousands of dollars. Okay, so we have this R function, this revenue function. Well, we can do things with that. We can find R prime, and R prime is just going to be the derivative of R, right? This is marginal revenue. And marginal revenue is the function that tells us if we make one more thing, if we make one more thing, if we make one more thing, how much more revenue do we get? So we're chugging along, we're making we're making some certain number of products. What if we do one more? In this case, the inputs, the X values, are thousands of dollars spent on ads. So we might ask ourselves, what if we spent another $1,000 on ads? And then what if we spent another $1,000 after that, and another $1,000 after that? Well, sure, the first few thousands of dollars that you spend on ads, you're going to get a positive marginal revenue, and so you know you're bringing in more money if you do that. But there comes a point where you spend more money on ads, and it doesn't bring in more marginal revenue. Well, where is that point? That's the point of diminishing returns. And we can find the point of diminishing returns by looking at the derivative of the derivative. Because as we well know, we can spend money on ads and we'll bring in more revenue, but eventually that fails. So if we spend another $1,000, maybe we get more marginal revenue, but then we spend another $1,000 and we get more revenue, but it's less. R double prime tracks how our prime is changing. And so we take the derivative of R prime, that's 800 minus 6x in the parentheses. And so this tells us how our prime is changing. And if we want to know the point of diminishing returns, we look for where R double prime is equal to 0. And that happens to be when X is, 800 divided by 6 is like 133-ish, right? Yeah. So what does that mean? Well, that means when we spend about $133,333 in ads, after that point, the money we spend isn't bringing in more revenue. It becomes senseless to bring in, to spend more than that on advertising. So what's important to recognize? Revenue is measured in dollars. Marginal revenue is measured in dollars in revenue per dollars in ads, right? Because revenue is measured in dollars, but the X values are dollars in ads. And R double prime is measured in revenue dollars per dollar spent in ads. And I hope you see how that all works, and I'd be glad to work through more of that when we gather in class. This is probably enough for now. Between the reading and the watching, I hope you've got a good handle on things. We'll see you when we gather.